Okay, hi everyone. So in this video, we are going to go through our chapter 3 vectors, exit pass. Okay, so this one will mainly focus on section 1 of the vectors 1 chapter, where we will focus mainly on collinear vectors and the ratio method or the ratio theorem or the midpoint theorem. Okay, so let's go through question 1 and see. So question 1, right, we have position vector of the points A, B, and C. They are given like that. Right? So even though they give in the form of ijk, right, you can also write this in terms of the column vector, right? So you have the three position vectors, so means these are OA, right? In case you don't know, these are OA. This one is OB. This one is OC. Okay, so we are going to find a unit vector parallel to the vector OB, right? So what we need to do is we'll just take vector OB, right? Find the magnitude and then make it a unit vector, right? So how do we do this? So first we're going to find the magnitude of OB. Okay, so the magnitude of OB would be like this. So this would be just 1 square plus 2 square plus 3 square. All together you have, and then square root. So all together you have root 14. Okay, then to find the unit vector, it is simply just, okay, because the vector is root 14 minutes long, correct? So the unit vector would be just to take the vector, right, divide by the length, or I take 1 over root 14, right? And I will have something like this, and this. So this can be my unit vector, like this, right? So you can write as a column vector to make it easier to see. Okay. Now for part 2, we have to find the values of lambda such that A, B, and C are collinear. So what do you mean by collinear again? So we have 3 points over here, A, B, and C, right? So if they are collinear, they lie on a straight line. So what do we have? We can look at vector AB. We can also look at vector AC. Okay, and they are a multiple of each other, right? And they also have a common point A, right? So technically, if they ask you to show that two vectors are collinear, we need to show a scalar multiple. So maybe vector P is a multiple of vector Q, right? And you also need to find a common point. Okay, you need to state the common point. For this case, they already give that the condition is collinear, so we're going to apply that one vector is parallel to another vector. So technically speaking, we will just pick AB is parallel to vector AC, right? But we can also write this in terms of a multiple of another vector. So I'm going to put a K over here. So then I declare what is my K for some constant, real constant K. Okay, so mainly something like that. Now, so what is vector AB? Vector AB, right, will be just OB minus OA, right? Then vector AC will be just OC minus OA. Okay, then what do we have? OB would be 1, 2, 3. OA is 3 lambda 3 and 3, right? K is this. OC and OA. So technically we should have done this in Emacs before. Yeah, it's just that now it's in 3D. So OA is again 3 lambda, 3 and 3. Okay. Now, if you want OB also can. OC minus OB also can. Doesn't really matter. Okay, as long as when they are parallel, it is a multiple of another. It will be a multiple of another vector because like this, right? Is like, let's say 1 times, then twice the length of the vector or 2 times the vector is also give you it also gives the same direction. Okay, so then let's simplify this. We will have 1 minus 3 lambda, negative 1 and 0 on the left. Then on the right hand side, we have, oh, this is a vector already. So I have a minus 1 minus 3 lambda, lambda minus 3 and a 0. Okay, now so with this, right, when you are in vector form, we can compare the component by component. So what we can do is we can compare the first component with the first component of the second vector. We can also then compare the second component of the first vector and the second component of the second vector like this. Okay, so with this we have okay. So with this, right, what we can do is we will have something. Okay, why like that? Okay, so we will have, 1 minus 3 lambda equals to k times of negative 1 minus 3 lambda. Why I keep breaking? Okay, so this is equation 1. We have another equation, negative 1 equals to k lambda minus 3. So this is going to be equation 2. Now, so this is a pair of simultaneous equation. What we can do is we can expand and we can solve, okay? But what we are going to do is we're going to do it the smart way. Okay, I'm going to take 1 divided by 2 so that I can cancel off my k after that. So it will be 1 minus 3 lambda over negative 1 equals to k 1 minus 3 negative 1 minus 3 lambda over k of lambda minus 3. So over here, very nicely, you can see that my k is being cancelled already. Very nice. Okay, so with this, I will cross multiply. Okay, I will cross multiply. Lambda minus 3, and then I get 1 minus 3 lambda. So on the left, let me expand this carefully. Okay, then let me rearrange everything to one side. 3 lambda square, 10, so minus 7 lambda, plus 4. So over here, 3 lambda, okay, then lambda minus 1. Okay, so over here I can solve. Lambda is equals to 4 over 3, or lambda is equals to 1. Okay, so this will form this will be solving for part 2. Okay, so making use of the property that they are parallel. Okay, so let it one vector to be k times another vector. Then we compare the components to solve for our unknown lambda. Okay, question 2. Okay, for question 2, we suppose that the points A and B have position vector A and B like that. Find the position vector of point P, which divides AB in the ratio 5 to 1. Now, so this question will make use of the ratio theorem. Okay, so what does the ratio theorem say is that when you have a vector, when you have a part, okay, dividing, let's say if you have point P, dividing this thing by m to n. Okay, so the vector, let's say OP, right? So let's say if I'm looking for this vector OP, right, would be OA and OB, right? Right, and it will be over a certain number. So how will the number work together is we will need to swap. So n would go this side, m would go to the other side. So this one would be n times of OA and m times of OB, right? And the denominator will be just n plus m, the total of the parts, number of parts. Okay, so we will swap the m and n, right, to get something like this. So this is what we know as the ratio theorem. Okay, so let us apply this to our working for part A. So find the position vector of the vector of the point P, which divides AB in the ratio 5 to 1, right? So my vector OP would be equals to, okay, I will set up OA and OB first so that I can look at the ratio later. Okay, over. Okay, so how do I do this? Now let's take a look. 5 would go to this side. The 1 would go to this side, right? So this would be 1 OA, okay, plus 5 OB. So this is 1 plus 5. Okay, so over here I will have 1 over 6, right? OA is 1, negative 1, 4. Then I have 5 times of OB, 7, negative 1, and 2. Like this. Okay, so all together, this should give me a 1 plus 35, so 36. Negative 1 plus negative 5, negative 6. 4 plus, negative. So 4 plus 4 minus 10, so also negative 6, right? Multiply in, I will get a 6, negative 1, negative 1. So this is the vector OP, right, for part A. Now for part B, over here, same thing. I have the line AB, right? And Q, you see the phrasing, Q divides BA in the ratio 2 to 3. So in this direction, the direction matters. So it will be in the ratio of 2 to 3. Okay, so the direction matters. Okay, so this 3 will go there, the 2 will go there. We'll need to swap. Okay, so how does OQ work? It's a combination of OA plus OB, right? But what ratio? Okay, so this would be 2 OA, okay, plus 3 OB. Okay, so at the bottom will be just the total number of parts. So over here, I pull the bottom out. So this would give me 2 OA, so 2, 1, negative 1, 4, plus 3 OB would be 7, negative 1, and negative 2. Okay, so add all of this together. Okay, let me shift this. Okay, shifting this here. Okay, so we have half of 2 plus 21, so 23. Negative 2 plus negative 3, so negative 5. 8 minus 6. So this is 2. Okay, so this would be our final answer for part B. Okay, so this is how we use the ratio theorem, which is very easy. Very, very easy, and something that you need to do as fast as possible. Okay, last but not least, let's look at question 3. Okay, so this is from a past year paper. So once again, the way to do well for vector is to draw the diagram. No matter how simple it is, draw the diagram so that you are very clear on what you are going to face. Okay, now so relative to the origin O, right, 2 points A and B have position vectors A and B respectively. Okay, so where A and B are non-parallel vectors, so they are not parallel. So the points C and D lie on the midpoints of OA and OB, so they will cut, right? The ratio they will cut half. Okay, so the line segments OD and BC, they intersect the point P such that, okay, OP, okay, cannot. Okay, such that OP to PD is in the ratio of lambda and 1 minus lambda. Okay, so first and foremost, let us find OP in terms of lambda A and B first. Now, OP is here, right? And it is actually a fraction of this whole thing OD. So I think what we can do is we can find OD first. We can find OD first, and then we can scale it back to OP. Okay, so what is vector OD first? So vector OD using the midpoint theorem, okay, it will be a combination of OA and OB. Okay, now then the ratio is 1 to 1, 1 to 1, like this, right? So over here, technically speaking, it will be just purely half of OA plus OB. Okay, so it is technically half of A plus B, vector A plus B. Okay, now then for vector OP, right, it is a fraction of the whole thing, right? So it is a lambda parts out of lambda plus 1 minus lambda parts of OB. Okay, so technically speaking, this is going to be lambda over 1, right? So I'm just going to put lambda times of OB. And OB is actually, OD, not OB, OD. Okay, OD. So what is OD? Lambda times of half A plus B, like that. So altogether, we can combine them to lambda over 2, vector A plus vector B. Okay, so this is the expression for OP. Okay, so not difficult. Now part 2. So show that the ratio of BP plus BPC is 2 to 1. Okay, so because we found a possible expression for OP, right? Right, and then so what we need to solve for this question is to find out what is our mu. Okay, what is our mu and what is our 1 minus mu, right? So that is the key thing to solve for now. Okay, however, where do we get information on this? Are we going to find OC and so on? But don't need, because we already found OD and OP, right? We already found this vector, and we found this vector using this means. Is there another way in which we can find the vector using vector OC and OB? Can or not? Technically can, right? Technically can, right? So technically speaking, it is also a combination of OB and OC. Okay, so for part 2, okay, so I will just highlight these 3 lines so that we can really see what's going on. Okay, so technically speaking, let's find out what's OC first. So OC is going to be equals to half OA, so half vector A. Okay, okay, now, so because we don't know what is the ratio of BP and PC, correct? We don't know what's this ratio over here, right? And then when you draw your diagram, right, like this part is actually non-existent yet, right? So what we need to do is it will be good to let this be U, and then this one will be mu, then the other part will be 1 minus mu. Okay, it will be a bit what do you call it? It'll be, so because the total part can be 1 unit, then this one will be just less than 1 unit and another one less than 1 unit, that kind of thing, to make it easier to calculate, right? If we were to use m and n, right, you will create more variable and it will be much more difficult for you to solve. Okay, so so the first thing is um I will need to let BP to PC to be mu and 1 minus mu first. Okay, so I need to let this happen first. Now then I will consider how to calculate the BP to PC. So the vector OP, right, using the ratio theorem, so this will go to B, right? This one will go to C, right? So here is a combination of OB plus OC over the whole thing like this. Okay, so let's take a look at what is this. So over here we have OB is in a ratio of 1 minus mu. Okay, OC is in a ratio of mu parts like this, right? Then all together at the bottom this will be 1 minus mu and then plus mu at the bottom. Okay, so over here I will have, because at the denominator, right, you can simplify the denominator to 1. Okay, this is going to be 1. Okay, so what I have over here will be just 1 minus mu of OB plus mu of OC. Okay, so let's write out the expression in terms of A and B. Okay, so I have 1 minus mu. OB is, what was OB? Or just B, vector B. Plus mu OC would be half, or mu over 2 of vector A. Okay, so now we have 2 expressions of OP already. We have one expression here, we have one expression over here. Okay, so equation 1, expression number 2. Okay, so what we are going to do now is we are going to compare the components of A and B, right? So comparing vectors. Okay, so comparing vectors. Now for vector A, the component for vector A, the first one is going to be lambda over 2. The second one is going to be mu over 2. So technically speaking, lambda is equals to mu. Okay, for now. Now, then for vector B, right, we on the left is going to be lambda over 2. On the right hand side, it is 1 minus mu. Okay, 1 minus mu. So I'm going to sub this in and try to solve. So because I'm looking for mu directly, so I will just replace this with mu over 2 equals to 1 minus mu. Okay, so actually BP and PC, right, we have BP and PC. So this one, what we're looking for is actually mu over 1 minus mu. Okay, right, so over here what we'll do is mu divided by 1 over minus mu, then this will be equals to 2 over 1. Okay, so why is it breaking? Okay, so therefore the final answer for BP to PC is just 2 parts to 1 part. Right, so this ends the video for question 2 for our vectors exit pass. Okay, so I hope this helps. Okay, bye bye.